Hello and welcome to another lecture in the course. Today we're going to state and prove Montel's theorem, something that we've been building up to over the last couple of lectures. This is section 6.2 in the book, and you can get the book in a link in the description. You can get a PDF for free or a paperback if you want. All right, we're going to state Montel's theorem in the traditional language. Partly because we don't have the modern language, and partly because it allows some fun jokes about, because we're going to talk about normal families, all these jokes about whether Montel had a normal family. All right, so let's suppose that U is an open set in the complex plane. A set of holomorphic functions on U is called a normal family if every sequence in F has a subsequence that converges uniformly on compact subsets, which is the standard sort of convergence. And we don't necessarily require this F to be closed in some sense. You don't need this limit, which is going to be a holomorphic function. We know that, but it doesn't need to be in this set F, right? So that's what we mean by normal family. Now, Montel's theorem will require some boundedness, and the right sort of boundedness is locally bounded. So a set, capital F, of function is locally bounded if for every point in the domain there is a disk of some positive radius r and a bound such that all the functions in F are bounded on that disk by M. Right? That's what we mean by locally bounded. Right? Locally, there's a uniform bound, right? All right. Well, this is just, just in case you don't remember this notation. It's the supremum of the modulus of F over the entire disk. All right. Now, in more model language, I'm gonna say what it is, but we haven't defined all of these things, right? F being a normal family is the same thing as F being precompact in the space of holomorphic function with a topology of uniform convergence on compact subsets. That's a little bit more of a mouthful, but that's a more modern way of stating this, right? But we're just going to use this definition and this more traditional language. All right, now there are sort of two ways of thinking about locally bounded, and maybe the more useful way is it really is the same thing. It's equivalent to being bounded on compact subsets, which really sort of plays well with we have uniform convergence on compact subsets. So, the right sort of boundedness that we want is bounded on compact subsets, right? All right, so here is Montel. So, suppose that we have an open set, and script F is a locally bounded set of holomorphic functions. Then F is a normal family, meaning every sequence in F has a subsequence which converges uniformly on compact subsets. Not necessarily something in F, but it converges, right? All right. So that's what I just said, right? That's the definition of normal family. All right. Now, we're going to apply Arzelà-Ascoli. So what we need to prove is that since F is holomorphic, this locally bounded business automatically gives us that F is equicontinuous, right? And then we can apply Arzelà-Ascoli, right? So consider a point P and a closed disk that's completely in U, right? So even the boundary, everything is in U, right? We have locally bounded, right? So, suppose that we have this estimate here, right? For all F in this set, script F. So that's a disk of radius R. So let's look on a disk of half the radius, right? I mean, if you if you draw this, right, this is a disk of radius r around P, right? So a disk of half the radius, right? Then, well, kind of obvious that if I'm anywhere, if Z is anywhere in the inside, right, then the distance to any point in the boundary, right, even to the closest points to the boundary, is at least r over 2, right? So armed with that, if we have a Z in this inside closed inside disk of radius r over 2, and f is any function in script f, we look at the modulus of the derivative of f at z. Well, we write down this is the formula, this is Cauchy's formula for the derivative, right? There's a square here in the denominator, right? We basically write it down as an integral over the boundary of this R disk, right? It's important that it's the R disk, right? We're integrating over the boundary of the R disk, right? Now, we use the triangle inequality for integrals, right? We take the absolute values inside. Now, here is where we use this inequality. Zeta, right, is on this boundary, right? So this is at least r over 2. Now we're doing 1 over that, right? So so we have the right inequality bounded from above by this guy, right? Now if you look inside, and we also bounded the f by m, right? Because f was bounded by m everywhere, but we only need it on the boundary, but who cares, right? So, all right. Now, if you look at this, there is no zeta in the integral anymore, right? So that's just the integral of a constant, right? So we have, we integrate this, it's gonna, we're gonna get a 2 pi out of it, but then we get this this 4 squared coming out, and there's an r from this integral, right? It cancels one of the r's. So I mean, if you work it out, this is that constant, right? That this integral evaluates to, right? So what we have is that the derivative at z, at any z, for any f, for any z in the ball of or in the disk of half radius, right, around P, is bounded by 4m over r. The point is this does not depend on this guy does not depend on f, right? Okay, so we're not really, in the end, we're not really interested in f prime. We're interested in this guy, right? In the difference of the values. That's the thing that comes up in equicontinuity, right? So f of z minus f of p. So we write it as an integral of the derivative because we know something about the derivative, right? So we integrate over the interval from p to z, on the straight line from p to z, and we bring the absolute values inside. We apply the estimate. We integrate, and this is going to give us the distance from z to p, right? So we get that this guy over here is bounded by some constant that doesn't depend on f. This 4m over r times z minus p, the distance from z to p. All right. So this means it's equicontinuous, right? Because if we want this f of z minus f of p to be small enough, we just pick a delta such that this whole thing is small enough, right? And this, nothing on the right-hand side depends on f, right? So we get equicontinuity. We're just doing it at p, right? And Arzelà-Ascoli applies to any sequence in f, right? And gives us a convergent subsequence converging uniformly on compact subsets. And we get that script f is a normal family. Montel's theorem is good for finding extremal functions. So what do I mean by that? It means that if we have some extremal problem, some quantity that's assigned to our functions, we can find the function that maximizes it, right? So, for example, we'll use this to prove the Riemann mapping theorem, just really where we're sort of going with this, which says that any simply connected domain that's not the entire complex plane is biholomorphic to the disk. And the way that it's done is that the biholomorphism is a map that maximizes the derivative at a point, right? That's the way that we're gonna prove it. And Montel gives us a way of finding that maximizer, giving us that maximizer. We can just, find sort of better and better, better approximation of the maximizer, and then Montel gives us that there is a maximizer. All right. Now, a commonly used version of Montel is Vitali's theorem, and we've seen an exercise that I talked about last time that's sort of related to this. Suppose that we have a domain and we have a locally bounded sequence of holomorphic functions, and let's suppose that we could suppose that it converges pointwise, but actually all that we're going to need is that it converges pointwise at enough points. And enough points means it converges pointwise on a set which has a limit point in U, right? So if E has a limit point in U, and this sequence converges pointwise on this set, then we don't need to actually pass to a subsequence. This sequence converges not just pointwise on U, it converges uniformly on compact subsets, right? All right, and proof is an exercise. All right, now let's do some more exercise. First one, very simple. Prove a converse, right? That if you have a normal family, then it has to be locally bounded, right? So it's the right sort of hypothesis that we want, right? Now, next thing is which is a good exercise is suppose that we have a normal family. Show that f prime are a normal family, right? If I take all the derivatives, that's a normal family. Now, the converse doesn't work. It's without some extra hypothesis. So try to find a counterexample to the converse, right? If I have, if this f prime, this set over here is a normal family, that, what other hypothesis I need to put on f to make it a normal family, right? And find an example where it doesn't work without that extra hypothesis. All right. Now, here's an example of trying to use trying to find extremal functions. So suppose that we have a domain and a point, and let's suppose for a moment that there exists a non-constant bounded holomorphic function on U. So something bounded, holomorphic, and defined on U, right? So prove that there is a holomorphic function into the disk with where the derivative at P is non-zero and actually maximizes the derivative over all holomorphic functions into the disk, right? So the max, first the maximum is non-zero, and there is a function that gets it, right? And then part B, show that this actually, this maximizer actually has to take P to 0. All right. So that exercise uses that's a good example of using Montel to find this, to solve these maximizer problems. All right. Now, the next exercise is actually kind of a neat, subtle thing. It's if you have a power series and its partial sums as holomorphic functions are uniformly bounded on on a disk, then the power series converges on that disk. Now it's not quite immediate. If you write down sort of the thing that you need to get bounded, to get convergence from just very, very basic results, it's really the absolute value was the with the things in the absolute values inside the series, and we don't have that here, right? So that's sort of so it doesn't quite follow immediately from the very basic result, but it follows from Montel's theorem, right? So all you need to know is that the partial sums are uniformly bounded, and that gives you convergence, right? All right. So next time we're actually gonna prove the Riemann mapping theorem. So we're gonna that's sort of like the big big theorem in one complex variable. If there's one theorem that any one complex variable course should have, it's the Riemann mapping theorem. So we're gonna prove that next time, not today. All right. So see you then.